Hello everyone, this is Doug, and in this video we're going to talk about the Hofmann rearrangement, sometimes called the Hofmann degradation, which is another way to make primary amines, but your choice of R groups on that amine is much larger. So let's take a look at that. So we are here, Hofmann rearrangement, right? R group can be almost anything, and it's used for making primary amines only. Limitations that the conditions are a little harsh, and you'll see what I mean in a sec. So making primary amines, right? Let's just go back a second. We said that you could do a simple SN2 reaction, right? Where your nitrogen just does a backside attack on whatever the leaving group is. And ideally, right, you'd get a propylamine in this case. But we were saying that the problem here is that you can get polyalkylation. Whoops. Polyalkylation. I always imagine, this is a total random thing, but for some reason, my program selects the whole slide to move when I do that. That's what that jiggle was. And I always imagine that you guys are freaking out because there's an earthquake or something. There's no earthquake. You're not going blind. It's just my pen is selecting the wrong thing. That's all. Polyalkylation. Alkylation is a problem. So I might get like this primary amine like I wanted, but I could also get the 1, 2, 3, 1, 2, 3. I might also get, when it's dialkylated, 1, 2, 3, 1, 2, 3, 1, 2, 3, or the tertiary one, or even the quaternary one, the quaternary ammonium salt, right? So I would get a mixture of amines and I'd have to fish them out. Now there are ways, if you have excess of ammonia, to try to make this work, but it's not as efficient, for example, as, say, the Gabriel synthesis, which only, see, like that, which only makes the primary amine. There is no opportunity for your free amine to come in contact with this substrate, with the alkyl group. And remember that for this, the big limitation is that this alkyl halide, and I guess it doesn't have to be an alkyl halide. It could be, right, it could be some other really great leaving group like triflate or tosylate or something. Alkyl halide must be able to do SN2 reactions. Right, it has to be a good SN2 substrate. That's the limitation of the Gabriel synthesis, because that's what happens, right? We take that H off, that nitrogen becomes negative, and then does a backside attack on whatever your alkyl halide or sulfonic ester or whatever it is. Now the Hofmann rearrangement, that's our new one. What's nice about the Hofmann rearrangement is that basically the R group can be almost anything. R group can be basically anything, right? So you'll notice, for example, this group right here, this could not have been made from the Gabriel synthesis, because you cannot have, right, like if I draw this out, this substrate here, right, if I tried to use this in a Gabriel synthesis, I'd have like a leaving group right there. But the problem is that this cannot do an SN2 reaction. Cannot do SN2. Right? It's on an aromatic molecule. It's on a furan. That hybridization right there is sp2, not sp3. Right? Remember that SN2 reactions can only work on sp3 hybridized carbons because you need to have a backside attack. Bond strength and bond lengths need to be consistent for again the backside attack on an sp3 carbon. So this type of molecules just can't do that. So the Hofmann rearrangement allows you a wider variety of R groups here. So we're going to take a closer look at that in a sec. So if we take a closer look at this reaction, right, I just want to emphasize that this is, again, it will only make primary amines, right? So only make primary amines, which is exactly what we have here. But what's nice about this is that the substituent can be almost anything, really, as long as it doesn't react with Cl2 or Br2 and it doesn't react with hydroxide, right? So it just cannot react. So I'll put as long as it does not react with Cl2 or Br2 or base. Right, so like if your R group had an alkene on it or something like that, you might be worried about brominating that alkene. Or if your R group had a carboxylic acid on it or something like that, you might be worried about it reacting with OH. So you just want to keep that in mind. Some other notes about this, for practical reasons, normally you see this set of reagents right here, the NaOH, Br2, water. We're going to see why in a minute, but usually this is an excess. You need a couple equivalents is not going to hurt you. So we will see that we regenerate some of it, but we're going to need a lot of it. I'm using Br2. Bromine's probably more common just because it's a liquid, and so it's a little easier to work with than chlorine, which is a gas. So that sort of has that advantage. So a lot of my examples are going to have bromine in them. So let's take a look at what this mechanism is. This is kind of a hairy mechanism. I'm not going to ask you to memorize this one. Probably. Nah, it's kind of, nah. It's not a great mechanism to memorize. It's a very kind of one-off, but it is interesting, so I want to show it to you. And so we've got hydroxide, right? We've got Br2. The mechanisms that I like for you guys to learn are the ones that show real general broad concepts that can be used over and over and over again, so you can figure out new mechanisms. This one's kind of odd, but I want to show it to you for a couple of reasons. So you've got a base here, and you've got your primary amide here, and I'm going to draw out. I'm not going to. The OH, you guys are savvy enough to follow that the OH is going to pluck off a hydrogen here, and those electrons from the NH bond are going to sit on that N. And that is totally reasonable, right? Because you have a resonance stabilized negative nitrogen. If it was not resonance stabilized, this would be probably just not reasonable at all. So you've deprotonated that, made some water. So I'll put plus H2O. And like I said, this is resonance stabilized. What we have here, now that I've taken that hydrogen from the nitrogen, it's negative now, and so it's a nucleophile. And what we see is that it then goes and attacks the Br2 or Cl2 if you're using it, and you end up brominating that nitrogen. So we form something that looks like this. Now, once we brominate it, right, and then plus Br minus, once we brominate it now, though, that nitrogen's hydrogen becomes even more acidic, right? Because halogens like chlorine and bromine and fluorine, they are electronegative, and so they're going to pull some electron density away. So now this second hydrogen becomes even more acidic, and we're able to pluck that sucker off now. And now here's a super weird step. This is why I kind of wanted to show you this so that you're aware that these things exist and they're not totally unreasonable intermediates. What's believed to happen here is that the bromine, oh, sorry, I forgot a negative charge, right? The nitrogen's negative. Resonance stabilized, but negative. And one way for the nitrogen to get rid of this negative charge is to put it on the bromine. And to do that, what that means is that the bromine simply leaves, which is strange because that's going to leave my nitrogen without a full octet, which, as you can imagine, is not super stable and going to lead to some weird things. This type of intermediate here, this, where you have a nitrogen, I'll draw this down here, a nitrogen with two lone pairs and one bond, that's called a nitrene. Right, it's a nitrogen, but it's an ene because it doesn't have all of its electrons, kind of like a carbene doesn't have all of its electrons. It desperately wants some more electron density. So this is kind of where the magic happens for this Hofmann rearrangement degradation thing. What we see happen, or what appears to happen, is that this lone pair can drop down, and this whole R group, the R group that we're all super interested in, sorry, let me erase that purple arrow. I just wanted a blue one. Are you going away? No. I will make you go away. There you go. I'm going to have this lone pair drop down. Come on, friends. And what happens is this whole R group migrates over, right? If that lone pair drops down, it's not like that carbonyl carbon can have 5 bonds. Yes, some electrons could go up, but what we see is that we have a migration of an R group, kind of like an alkyl group migrating when you have carbocation rearrangements or something like that. So we see the whole group migrate over, but that leaves us with an oxygen that's double bonded to a carbon that is now double bonded to this nitrogen, but this nitrogen now has, in this case, that furan group. Did I? Yep, I think I'm okay. I'm okay. Just checking my conductivity. I thought I might have messed it up, but I'm good. But that's not good. So we've got double bond, boom, boom. There we go. Right, so now everything has a full octet, right? And the idea is that that's the driving force behind this reaction, is to keep the full octet. So if I do a little rearranging here, then I'm good. I'm everything's satisfied. Everything was neutral before, everything is neutral now. We just rearranged how things were attached. Now, I still have some hydroxide. And that hydroxide is going to attack, right? If you look at this molecule, partial negative, partial positive, partial negative, it's going to attack this carbon in double bonded to the O and the N. And it's going to cause the electrons to, well, they'll be resonance stabilized, but I'm going to draw it on the N because that's going to get us to our product quicker here, and you'll see why. So let's see, we have O double bonded to a carbon with an OH, which should look a lot like a carboxylic acid, and a nitrogen with 2 electrons that's now negative, and it's attached to the furan. And this, again, is resonance stabilized. I'll draw the resonance structure. So it forms a relatively stable-ish anion, right? Oxygen spread out between an O and an N. Not as good as 2 O's like in a carboxylate, but still reasonable. And then what we see is a proton transfer where this nitrogen gets this hydrogen. Giving us this molecule. Right, so I've moved the hydrogen over. It's just a proton transfer step. But now you have this unstable carbamate, and they tend to fall apart pretty easily, especially under basic conditions. And so this lone pair can drop down, and it actually kicks its whole self off as carbon dioxide. That's where this carbon dioxide comes from, and leaves the electrons on the nitrogen, which will give us another negative nitrogen. I'm sure at this point you all are like, I'm so glad I don't have to memorize this. But you can just for fun if you want. So I have a negative nitrogen, and like we've shown in multiple steps, we have water around. And so as soon as you form this negative nitrogen, it's just going to protonate in water to give you your product. So that's the whole hairy mechanism of how this thing occurs. I have no idea if Hofmann was like, I think this makes sense on paper, I'm going to try it in the lab. Or if he just was working with some amides and these reagents, maybe he's trying to do an alpha bromination or something like that, and he just saw that this happened and then tried to backtrack and figure out maybe what the mechanism was or what the limitations were. But here's the whole mechanism, right? So here's how we generate CO2, and we basically migrate that whole R group, right? This whole R group here migrates onto the NH2. That's what you get at the end. The whole R group migrates over, and you end up expelling carbon dioxide. It just bubbles away. One-way reaction doesn't come back. And what's really cool about this is that, like I said, we don't have to worry about it being that R group being a good SN2 substrate because there is no SN2 reaction going on. And when that R group moves over, this example doesn't have chirality or any stereochemistry to it, but when it does move over, it retains all that stereochemistry. Right, so if you were going to make a primary amine that had stereochemistry in it, If you did a Gabriel synthesis, that stereochemistry is going to get inverted because it does a substitution. If you do a Hofmann, it gets retained. It's, if it was R, it's going to stay R because the whole group just migrates over. There is nothing doing a backside attack or anything like that. So like I said, only primary amines, substituent could be anything. So if I go through these, right, this one's a primary amine, so I could use Hofmann for that. This is a secondary amine, so can't use it for that. Tertiary amines, nope. This is a primary amine, and that's a primary amine. So really, any of these primary amines would be possibility, right? You could use Hofmann for any of them. And the idea is that you just make the amide with that group on it. So let me show you what I'm talking about. If I wanted to use the Hofmann rearrangement on this one, I would basically just redraw the R group that I wanted. At this carbon, I would add an additional carbonyl and then make sure that it's just the primary amide, right? So this molecule, if you expose it to the Hofmann molecules or the reagents, it would form that product, right? Because you're basically just going to get rid of the carbonyl, put the nitrogen at that spot. For the primary one, same thing. I just need to insert a carbonyl between the group that we're talking about here and the NH2. So I'd need that amide to make that one. And then lastly, for this one, you would just use the benzamide to make that product. All right, so if I want to make any of those primary amines, I could use the Hofmann rearrangement like that. So here's some examples. Again, this would be a good place to pause. See if you can do these four. The first three are just fill in the box. The last one's a synthesis type problem. It's going to take a couple of reagents, a couple of steps to get from point A to point B. So go ahead and pause, take a minute. I'll come back in a sec. Okie doke. So first one, right? Basically all we're doing, like we said, you take that amine, you take whatever was attached to the carbonyl, and you slap it all together. So this apparently would make an isopropylamine. Boom. It's a primary amine. The R group's secondary, which means it's not so great for SN2, so probably just doing a straight up alkylation or just doing the Gabriel synthesis wouldn't be great. Here we have another one, primary amide. We got this whole group, and I'm just going to attach that. It retains that point of attachment, right? So I'm going to redraw my aromatic ring here and just put the NH2 there, right? The carbonyl just goes. That's the part of the CO2. Same thing if I want to backtrack with this one. So I need to redraw this piece. I got the cyclohexyl piece. And then one carbon that I want to keep. So that means I need to add another carbon for the carbonyl and NH2 to make that. That would be that product. Now for this last one down here, looks like I'm starting with an alcohol and I end up with an amine, primary amine. This whole video obviously is on Hofmann, but the thought process that you should go through here is that, okay, I'm making a primary amine. I see that it is not a good SN2 substrate, right? Because the group that it's attached to is secondary here. And so that means probably I'm going to do the Hofmann. Probably going to go the Hofmann rearrangement. But if I do that, that means I need an amide. Right? I need a carboxylic acid derivative. I need an amide. I don't start with an amide, but I know how to turn it into an amide because I've got an alcohol here. I know I can oxidize it up to the carboxylic acid and turn it into an amide from there and then do my Hofmann, which is exactly what you should do. All right, you should just oxidize the bejesus out of this. So use like the Jones stuff. So I'll put the chromic acid in this case. It should be 4. H2CrO4 with some acid or water. So that would give me that. I know that I could do step 1, add SOCl2 to turn that into an acyl chloride. And then step 2, I should just be able to bubble through some amine, some ammonia to make this molecule. Right, so the acyl chloride is super reactive, so any amine I add to it will make the amide. Boom. And then the last step, I can just do my Hofmann stuff. So I'll add Br2, NaOH. There'll be some water present, and then it should do and heat it up, and that should do my Hofmann rearrangement, just like that. So that's one way to make that amine. Anyways, I hope that this video answers some of your questions. It is a useful way to make amines. Very, very classic way. Hofmann's big fancy guy, so we have to all learn all of his reactions. Anyways, do lots of practice. Let me know if you have any questions. Good luck.